If you were being sent to a deserted island and can take only one equation with you, you're packing your bags, you only got room for one equation, this equation might well be your choice. The derivative from a to x, ft dt, is equal to f of x, and in this podcast, we're going to introduce the fundamental theorem of calculus, which that equation is showing you. So let's talk a little bit more about the fundamental theorem of calculus. So here's some fundamental theorems. Other branches of mathematics have a fundamental theorem. Arithmetic does, algebra does, geometry doesn't, but we have one that maybe could be the fundamental theorem of geometry. So let's look at these. Fundamental theorem of arithmetic: any positive integer can be represented in exactly one way as a product of primes. It allows us to break down numbers, allows us to take square roots, refactor numbers. So any number can be represented one way as product of primes. That's the fundamental theorem of arithmetic. Fundamental theorem of algebra: every polynomial of degree n has exactly n zeros, right? Some of them could be real, some are complex, but it has n zeros. Could even have repeated zeros. Fundamental theorem of geometry: no theorem wears this title, but perhaps the Pythagorean theorem deserves to be called the fundamental theorem of geometry. It's probably one of the most important theorems from geometry. But now we're talking about the fundamental theorem of calculus. So fundamental theorem of calculus gives the precise inverse relationship between the derivative and the integral. So we're joining these two together. It was Newton and Leibniz who exploited this relationship and used it to develop calculus into a systematic mathematical method. In particular, they saw that the FTC, fundamental theorem of calculus, enabled them to compute areas and integrals very easily without having to compute them as limits of sums. So you can thank Newton and Leibniz for not always having to do to compute areas under a curve and your definite integrals as limits of sums. Without them, you might have to do every single one of these as a limit of a sum. So calculus has two parts, has differential and has integral. Right? Differential looks at instantaneous rate of change. Integral looks at area under the curve. We can combine those two with the fundamental theorem of calculus and now look at total accumulated change using both parts. The key to understanding this theorem is to know and appreciate that the definite integral is a limit of Riemann sums. Right? And we've gone over this notation several times. Right? So our integral from a to b, f of x dx, is defined to be a limit over all partitions of a and b. Right? It's the limit of all of, if we were to take an infinite number of infinitely small partitions, right, and take that limit, right, we would have our area under our curve. Right? Fundamental theorem of calculus allows us to compute that in a different way. But it's important to understand that the definite integral is actually a limit of Riemann sums, even if we compute it a different way. So we're looking at here in this part of the this podcast, we're looking at part of the fundamental theorem of calculus, and we're looking at the evaluation part. So if f is continuous on AB and big F is any derivative of f, then the integral from a to b, f of x d of x, when we integrate and we find the antiderivative, we can evaluate from those two, from a, we can evaluate on a and evaluate for b and subtract our lower limit, what we get from plugging in our lower limit, from what we get from plugging in our upper limit. Okay? But notice I underlined that word, and you should too. The function has to be continuous. All bets are off if the function's not continuous. Right? We've only dealt with continuous, or at least functions that were continuous on the interval that we're working on. Now we might see some functions that are continuous. So basically, this theorem allows you to find the area under the curve by integrating the function. The parts of the fundamental theorem of calculus, by the way, are not consistently labeled. One book, the evaluation is part 1. In another book, the evaluation is part 2. The part 1 and part 2, who's part 1, who's part 2, doesn't matter. In this lesson, though, part 1 is going to refer to the evaluation part. So we're just talking about evaluation here. So fundamental theorem of calculus, if a function f is continuous on the closed interval AB and big F there, what we get is an antiderivative of little f, our derivative, on the interval of A to B, then we can simply find that area under the curve by integrating and evaluating. And it's always going to be what we get for when we plug in the upper limit minus what we get when we plug in the lower limit into our integral. Right, so here, fundamental theorem of calculus, if f is continuous on AB and f of x is an antiderivative, right, this is going to give us, we're going to be able to evaluate now, and we've been doing that in class, right, without necessarily taking a limit of Riemann sums. Make sure you use the proper notation, right? So here, when we integrate f of x dx from A to B, you should notate that just the way I have it here, and I have it underlined in red. Oops, there we go. I have more underlined in red now. All right, you should notate it like that. Write down what you're plugging in. That is standard notation there. And then you're going to plug in your upper limit and plug in your lower limit in everywhere you have an x, right? So 2 steps in calculating, evaluating our integral, our definite integral here. Number 1, you have to find the antiderivative. And number 2, you're going to evaluate the difference. Here's a little proof. We've seen the proof. I've gone over it kind of very, very briefly. It's not something I'm expecting you to, I just want to introduce you to that. And I've introduced it to you in other lessons and showing you how that when we evaluate and take the difference of our integral, that really is that limit of those Riemann sums, right? And so these would, all of them would cancel off except for f of b and f of a. All right, so it's not important. I just want to introduce you to the proof just so you've seen it. It's not something I'm expecting you to necessarily master and be able to do yourself and be able to prove this to be true. I just want to introduce to you why, so you have some understanding of why this works. But we're going to mostly just be utilizing it. Okay? So guidelines for using the fundamental theorem of calculus: provided you can find an antiderivative, you have a way to evaluate a definite integral without having to use the limit of a sum. Of course, if I ask you to use a limit of a sum, you're going to use a limit of a sum, but now you have another way. And we're actually going to be using this way much more than a limit of a sum. When applying the fundamental theorem of calculus, the following notation is used. Please make sure you notate this exactly the way you see it up here. It is not necessary to include a constant of integration, c in the antiderivative, because they cancel out when you subtract. And actually in a later lesson, I'll just kind of show you this is why the c is not needed. It really does cancel out. So given a continuous function defined in a closed interval AB, dividing the interval from A to B into n subintervals of equal width, the definite integral is the value of the Riemann sums as the number of rectangles approaches infinity. That is what the area under the curve is. That is what the definite integral is. But this here, can't point, you can't see it. This here, that is also the definite integral. They are one and the same. We're going to look at one example, and then I have a bunch more examples and some properties of integrals on the next podcast, and then I'll be wrapping it up with a third or maybe fourth podcast. But let's do a simple problem here before I close this podcast. All right, so we want to integrate and evaluate, find the definite integral here. All right, so we're going to integrate x squared. That's going to give us, just put it below here, that's going to give us x cubed divided by 3. And we're going to evaluate that from from 2 to negative, or negative 1 to 2. And so I'll plug in 2 cubed divided by 3 minus, and I'm going to put parentheses here because I'm going to have two negatives, negative 1 cubed. Actually, I could put parentheses here too if I wanted. It's not going to matter either way. Either way, that's going to be negative, divided by 3. All right, and now we'll simplify. So this is 8/3. Oops, what happened to my, we lost our fraction bar. 8/3. We're going to have, this is just going to be a negative still going to be negative 1. All right, so we have minus a negative 1. That's plus 1/3. That means our area under the curve is 9/3, or what a pretty number, 3. And that's all there was to this one. All right, thanks for watching. We'll do some more on the next podcast.